Yeah, so sorry for not recording. We are gonna, yeah. Sorry for the people who are gonna follow this later, but there will be slides. I should probably just put recording be done. The thing is that I always start this early, and I don't want like stupid stuff that we talked before class to be recorded. But okay, yeah. Anyway, so we are talking about the diffraction. So for the people who are watching this later, we're talking about the diffraction using Fourier transformation now. So basically, what diffraction does is that it changes the angular distribution of the light. The light always comes when we are looking at one wave. Light comes from one direction, and then strictly speaking, this delta function in direction gets spread into some other distribution, which will depend on the shape of our aperture and so on and so on. And the bigger our aperture is, smaller these disturbances, let's say, are. And here is one example of how that works as a Fourier transformation. So our slit would basically correspond to this, and here there are the real values, and I will put the Python code used to make this online. So on the left-hand side, we have the distribution of the electric field in the plane of aperture. And it is this way because we are only allowing the electric field to pass through the slit, and elsewhere there is no electric field, right? Now, and you can try this on your own, if you take the Fourier transform of this equation, you're gonna get sync. And this is the electric field at the screen. And strictly speaking, it never drops exactly to zero, right? You see that it's modulated, that it's strongest here in the center, right, at zero, and that it falls off very quickly, but it still exists there, right? So what I want you to try to do now is, and even if you did this before, it doesn't matter, do it and tell the other ones, take 5 minutes to think about how you would use Fourier transformation to solve the problem when we have two slits. So we have two slits, which means we have two top hat functions at different locations. How would you do that to basically calculate the diffraction pattern when you have two slits? And to help you, yes, Jen?
Isn't that 1/meter?
No, because I went to, well, because this is, it's not literally Fourier transformation, right? Real Fourier transformation give you 1/meter, but then you multiply by k, so you get to dimensionless quantities, which means angles, and then finally you multiply by the distance to the screen, so you go basically from meters to meters. So yeah, if this confuses you, don't pay attention to the variables. There are a few constants going in between. And so just to remind you, this is, and to give you some ideas, this is the difference between the one slit and two slit diffraction pattern. So in one slit we have wide maxima and then another wide maxima and so on and so on. In the two slit case, it's modulated by these high frequency variations. And another useful thing are the properties of Fourier transforms, right? So Fourier transform has these very useful properties. One is the linearity. It's a linear operation, so sum of Fourier transform is Fourier transform of the sum. It scales in this following way, and something that might be useful is this convolution property. So if you do convolution of two functions in real space, whatever it is, and then do Fourier transform of that, it's the product of the Fourier transformations of the individual functions. Okay, so Fourier transform somehow makes convolutions easier. So I'll give you a few more minutes, and then we can hear ideas. Just sketch it, you don't have to derive it. So also, I mean, I wrote this as a Fourier transform here, or there are a lot of arbitrary constants that you have, and there are various definitions of Fourier transforms. So, but in principle, the important thing for us is e to the minus ak standing in front. Ak theta. Okay, so once again, for one slit case, we had one top hat function, and as a result, we got sink. So the question is what we would get, how we would approach the problem of having two top hat functions, just at different locations. Okay, let's hear the ideas.
So your two top hats can be written as the top hat convolved with two delta functions, if that helps.
That helps a lot.
And then you've got, so you take that into Fourier space, and then you've got, that's convolution. So in the Fourier space, you're going to have multiplication of the Fourier transform of two deltas with the top hat.
Very good. So in case the people didn't hear, I don't know if microphones are picking up everything. And actually, we can move to the solution, and that is exactly right. So these are two top hat functions, and basically having two top hat functions is a convolution of having two delta functions and a top hat function. Now, having two delta functions is basically Young's double slit experiment, right? Yeah. It's cosine. While having the Fourier transform of the top hat function is a sink. So what we're going to have on the right-hand side is going to be a product of a cosine and the sink. And the electric field would look something like this. This is the product of the cosine and the sink. Of course, the cosine and the sink don't have the same arguments. The sink depends on the width of the slits. The cosine depends on the distance between the slits. And then when we take the square of this, it looks something like this. So this distribution here is basically a sink modulated by a cosine of the higher frequency, which corresponds to the lower image here. Okay, pretty cool. So now it's good to remind ourselves what convolution actually is. So convolution, I denote it here as a star, and the star is going to have a variable number of, however you call these little things, is basically this kind of product. So I center my function f at some location, then I multiply it by the other function, which has argument x prime minus x, and then I integrate over x prime. So convolution also, strictly speaking, changes the coordinate. And very often when we talk about the convolution in context of astrophysics, it performs some sort of smoothing on our data, right? So here you have a so-called sawtooth signal, which is very sharp, and then you want to convolve it with this sort of kernel, we usually call it. What you're going to end up is a signal which looks like a sawtooth signal, just sort of smoothened and broadened. And this is exactly what convolution will do to our data. So we'll have it in few aspects. There's convolution due to the presence of the spectrograph slit. There is convolution due to the PSF of the telescope, and so on and so on. Okay. And now there is an interesting thing. We can start increasing the number of slits, and our diffraction pattern is going to change. And you can see here that for one slit we get this very broad minima. As we move to multiple slits, we have more and more clear presence of the maxima here. And to plot it in a different way is going to look something like this. So if I have 5 slits, each 0.1 millimeter wide and separated by 1 millimeter, my interference pattern or diffraction pattern, however you want to call it, is going to look like this. If I increase the number of slits, these secondary maxima are going to become smaller. I'm going to have more of them, but they're going to become smaller. And my primary maxima are going to be more narrow and stronger. Right? And this is the equation here if you want to refresh your optics knowledge and try to derive that one. But this is basically how the diffraction gratings work. So now a question for you. We were talking all the time about monochromatic plane waves, and I said that frequency of the light doesn't matter and so on and so on. But now I'm talking about the diffraction grating, which is an instrument used for the spectral analysis of the light. How do we use a diffraction grating? What do we want to do? So what is the diffraction grating going to do?
You're still talking about monochromatic.
No, I'm not talking about monochromatic anymore. So now we have what happens now if I take the different wavelength and let it go through this system of slits? Are the maxima going to have the same positions? No, exactly. So the key is the fact that all these diffraction experiments, phenomena, they're not only experiments, change with wavelength. So now if I took this system of, 10 slits, and I let two different wavelengths go to the system, these wavelengths are going to have the maxima located at different positions. So we're going to go deeper into this, and when we talk about spectrographs, and we're going to see exactly what happens there and what the order means and so on, and how we use these things to analyze the light. Because as I said, what we get is many waves of coming from different directions and having different wavelengths and so on and so on.
You might
Yes.
want to go to the previous slide. Then.
Yes.
It's easier. I think you might want to notice that the transparency, that the transmission or the intensity of each peak is different.
Yes.
It's modulated by.
Yes, absolutely.
So as you go to you can go to infinity, but as you go to infinity, those go to zero.
Yeah, the maxima are going to be smaller and smaller. Yeah, exactly. And I just put this here to see that we can exploit diffraction in some way. So here we are using the wave nature of the light to design an instrument that separates the light. However, what we're going to talk about for the rest of the class is we're going to talk about diffraction as a nuisance and a sort of problems in our telescope. So here we're going to talk about diffraction of circular aperture. So since the plane wave that reaches our telescope is infinite in x and y, strictly speaking, when it encounters the primary, which for simplicity, just imagine it's a lens and that it's there at the beginning of your telescope, there's going to be a diffraction happening there. Okay, and here is an example of a diffraction in a circular aperture, and that kind of diffraction would look something like this. So you would have this strong primary maxima here, and then this ring-like pattern around. And this central maxima here is what we call aridis. And the equation for this looks something like this. So in the case of, now I cannot. When we had a slit, it was we had a sinc function. Now we have sort of a counterpart of the sinc function in spherical or in polar coordinates, so to speak. And instead of having sine here, we have this j function, which is called Bessel function of the first order of the first kind. Right. And it looks in a way similar. The shape is to the eye, it's similar to the sinc function. The locations, of course, and the strengths of the maxima and minima are different. Okay, so we see again that the argument here, I just changed it so that we can emphasize the difference. That the argument depends again on the A, and A in this context is the diameter of the aperture. And again, the same is going to be true as we spoke before. If we somehow made A infinitely big, this area disk would shrink this whole diffraction pattern would shrink in a point. We would have no diffraction. If we made it infinitely small, we would basically get, uniformly light everywhere, we would get our aperture would turn into a spherical source. So that's one of the reasons, and for the rest of the class we're going to talk about consequences why we want to have big telescopes. So very often it seems, I mean, the saturation in these images is made so in order to see the secondary maxima you need to emphasize, you need to saturate the primary one. In 3, if you were to visualize the point spread function or this area disk, which is basically the interference pattern of a circular aperture, it would look something like this, right? So this primary maxima would be really, really strong. The secondary ones would be significantly smaller, but still detectable, right? And this is, of course, since your aperture is azimuthally symmetric, then also your interference pattern has to have azimuthal symmetry, right? So let's take a look at this pattern a little bit. There is, if you were to just plot intensity depending on rho, it would look something like this. And the most important location for us is the location of the first minima, right? And the first minima is located at 1.22 lambda over d, where lambda is the wavelength of the light, and d is the diameter of your aperture. So bigger d you have, more narrow this maxima is, and less diffracted your light is. And you can see some interesting things here is that, for example, the relative intensity of the second maxima is relatively small, it's like 1%. And maybe for you now it seems very small, but strictly speaking, this also contributes, right? If you have multiple sources or extended sources of dramatically different intensities, then this can spoil your signal a lot.
Oh, right. Is that control or is it integrated over?
That's the intensity of the peak.
This is intensity. This should be the intensity of the peak.
No,
But the area of that
is
ring.
larger.
But the area is much bigger.
The area is bigger.
Yeah, I think the power contained in the primary one is like what, 83%, something like that.
So
Yes. So there is still 17, or let's say roughly 20% contributing by the secondary ones. Actually, we'll put it in a homework to have different kinds of convolutions and so on. So you can try a lot of things to see how much it really matters. I mean, also part of it we'll do next class. We'll do these things hands-on. So what happens now when we have two sources of the light? You maybe remember this sketch from the previous class. So we had the situation of two bundles. So here we are talking about geometrical optics. So these are two bundles of the rays that are encountering the lens from different directions, and they're focused in two different points in the focal plane, right? So now I'm going to make the situation a little bit more complicated, and I'm going to treat these not as bundles of rays. I'm going to treat them as wavefronts, which means each of these wavefronts can diffract on the aperture. So how this would look, clumsily sketched by me, is that now, because we also have the diffraction of the aperture, these rays are not focused anymore in single points, but they are smeared and they are basically transformed into some distributions in the focal plane. And this is the reason why the stars, when you look at them, have finite sizes on your CCD, even when you focus the best you can. It's not that you didn't focus well enough, it's that this delta function in direction is spread into area disk, and what you are basically measuring on your CCD when you look at the stars is the area disk. So as we said previously, almost all of the stars are basically point sources, but when you use a small telescope and you look at them, they're all going to be some, smudges. Not because your focus is bad, but simply because your telescope creates big area disks, right? Does this make sense? Yeah. Of course, here I sketched only the primary maximum. I mean, I don't draw so well. Right. So now we get to this thing called Rayleigh Criterion, which basically tells us, and obviously at some point, if I look at two very, very close sources in the sky, these things are going to overlap. If I look at two sources separated from each other, they're going to be well resolved. So basically what we want to have is we want to, in order to resolve 2 point sources, we want them to be separated basically by this amount. So we want the second source to be placed at least at the minima of the area disk of the other one. Of course, we can't really plan it ahead, right? This depends on the fact how spaced the things are in the sky, right? If the 2 stars are close and our telescope can't resolve it, it can't resolve it. We have to build bigger telescopes. Yes.
But if you sample it, if your detector samples it well enough and you have enough light, you can see very well the diffraction pattern on the last one. It's very elongated compared to the first one.
That's true to some extent. You mean we would be able to see that there are 2?
I mean, if you give me, sorry, if I know the PSF of the instrument really well,
yeah,
and you give me the last
Yes.
one, and you tell me are there 2 point sources?
Yeah, you will be able to say there are 2 point sources. I agree with that. Yeah. So strictly speaking, if you have this image here, and this image is what? Speaking in language of Fourier transform, or speaking language of diffraction. This is 2 delta functions, right? Convolved with your PSF. Oh, we're going to get to that later, but okay. So sure, in principle, you could do the deconvolution of that. The thing is that you would then introduce some noise into your measurement. But yeah, maybe you would be able to reconstruct. We can actually try that. But yes. In principle, you're right. Yeah, but then it requires that we know the PSF of our instrument perfectly, which we don't, because it's not only the telescope that contributes to the PSF, it's also the atmosphere. Okay, cool. So this now maybe also allows you to appreciate why wavelength is also important in the observations. Why, when we, for example, look at blue wavelength, sun will, strictly speaking, be sharper, because these the diffraction is simply different. This also allows you to understand why the radio telescopes have so ugly pictures in a way, right? We have to create huge, well, they don't anymore, right? But one radio telescope, which can be hundreds of meters wide, is still going to have much poorer images, let's say, or angular resolution than the visible one. Of course, the fact that radio telescopes work with very high wavelengths allow us to make better interferometers. So eventually we can make an interferometric system which emulates having huge telescope, and then we have very small spatial, very, very high spatial resolutions. And for example, this case, it was last year, right, when they observed the event horizon of the black hole. That was done with the huge radio interferometric observations. Okay, cool. So now what happens when here we took a look at Rayleigh Criterion and we have 2 sources, but sun is not 2 sources. Sun is an extended source. Simply speaking, it has infinite points, right? So finite sources are in a way infinite ensembles of point sources. So each of the points is gonna spread because of the angular resolution of the telescope, and then what's basically going to happen is that our original image is going to get smeared by the PSF of the telescope. And in this case, what we basically do, and I want you to think a little bit about this, is that we can just, and I'm going to say it in advance, we can just take the image, the original one, that would be there if there was no telescope, and convolve it with our PSF. So we are basically adding the intensities of these point sources. Why are we allowed to do it? Or said in a different way, why am I allowed to just sun these area disks of 2 stars? Why are they not interfering with each other?
Because they're incoherent?
Because they're incoherent, exactly. So all this diffraction only is true for coherent waves. When we look at the different points on the solar surface, they're always going to be incoherent. And that makes our situation much, much easier, because we can just say, okay, there was this original image of the sun with infinite resolution, and I just take it and convolve it with the PSF of my telescope to get what I see. Of course, this is not what we're doing. The nature is doing that. We need to, work with that, right? So So strictly speaking, if you look at this case again, the purple rays and the red rays are all coherent with its own rays, but are mutually incoherent. So it's just that their intensities that are being added. So always have this in mind, that when you have coherent sources, you're adding the electric fields, and that's where you have all these exotic phenomena like interference, diffraction, superposition, which is basically just superposition. While when you have incoherent sources, you're just adding intensity. So if I have two lights, regular light bulbs, and they are both shining, the intensity everywhere is going to be 2 times the intensity. But when I have two lasers, and lasers are so coherent that even two separate lasers can interfere, then I will have I will add their electric fields, which are then added as waves. So somewhere I'm going to have 4 times the intensity, somewhere I'm going to have 0 intensity. Yes?
How did Young did he?
I actually still don't know, because Young, no, I know what he did, but probably he didn't really get this book example. So what Young did is he had, before having two slits, he had another screen with a single slit. So sun was falling on one screen. There was a small pinhole. The radiation emerging from that pinhole was then coherent, and then it was hitting this two-slit system and then producing the diffraction. Cool. So let's see what would the convolution do to our ideal signal. So unfortunately, we don't know how the sun really looks in infinite resolution, but we have some MHD simulations which are done in resolutions that are very high. So here I think 1 pixel is 20 kilometers or less, maybe even. But if it's 20 kilometers, then it is close to resolving this, right? And so this is how intensity and circular polarization. We didn't talk much about polarization. We're going to talk about polarization, about polarimetric measurements soon, and then later we're going to use polarization to infer many interesting things. But now you see a lot of structure in this image. But then when you look into the telescope, and now I'm going to look through at this image with a telescope of approximately 1 meter aperture, it's going to look smeared, right? So now I suddenly don't see so much detail. Don't pay so much attention to the lower image, because I did also something else to it, so it's not just smearing. But already on the upper image, you see that detail is lost, right? For example, here in the middle of the granules, there is this numerical noise, which looks like this fringing here. When I convolve it, it disappears, right? So simply the things are not so well seen. And in principle, when you look at the intensity only, the thing that this application, the PSF, is going to do to your data is that the contrast is going to be lower, right? So you could also imagine that now if I took wide enough PSF, if I made really, really poor telescope, I might smear this image so much that I don't even see granules and intergranules anymore. And the situation is particularly bad when you have measured quantities which can be positive and negative. So for example, the circular polarization can be positive and negative. And smearing in that case can lead to complete cancellations, right? If I have positive circular polarization in one point and negative in the nearby point, and my angular resolution of my telescope is very poor, so it can't resolve these 2 points, it's simply going to add these 2 things together and completely erase any signal. So even though I had magnetic field, both positive and negative here, what my telescope sees is no magnetic field. And
a positive and a negative star.
Yeah, exactly. It's like a positive and negative star, yeah. So star and anti-star. So actually, here you have some of the examples of the finite spatial resolution acting on the inferred quantities. So what I did here is we had the original data cube, which had its own velocity, magnetic field, temperature, and so on. I calculated the observable, which means intensity, polarization, and so on. And then I applied some of the methods that we're going to apply together in the second part of the course to retrieve back the velocity. And you see here that the retrieved velocity is much less resolved than the original one. And this is particularly annoying when we talk about a magnetic field. So here you see a lot of positive and negative magnetic fields in the field of view. Here you see it smeared out. And it's very important for the energy balance because the energy, the magnetic energy scales as the square of the magnetic field. So a magnetic energy doesn't care about the direction, right? So basically what I see in the right image here is I simply have less magnetic energy than in the left one, right? And that is why, and I hope we'll get the chance to talk about it, why, for example, Hanley observations and analyzing using various methods to detect magnetic fields might prove to be very important, because if the magnetic fields are mixed on very small scales, then maybe we cannot even see them with dickeys. Okay. But that's not the topic of today's lecture. So let's talk a little bit about the differences with resolution and sampling, and one misconception that we always, one thing that very often slips through cracks, and we're going to reach it at the end here. There is this useful theorem, or even if we don't understand it fully, we can use it as a rule of thumb, is that if you have observed frequency, if you have any, let's say, a phenomena happening at some frequency, we need to sample that frequency at double the rate, right? So in context of our telescopes, that means if our spatial resolution is, for example, 1 arc second, we should sample it at half arc second. So if our pixels should cover 1/2 arc second in the sky. For dickeys, that basically means that if, I don't know, the theoretical resolving power is, let's say, 0.0, okay,
Number.
0.04 arc seconds, let's say, at given wavelength, then it means that our pixels need to be 0.02 arc seconds big in the play of the sky, right? And this is true not only for the angular sampling. This is also true for spatial, for temporal sampling, and also for wavelength sampling. So we're going to see when we talk about the Fourier parallels in the spectrographs, we're going to define spectral resolution of our instrument. And also in the case of spectrograph, spectral resolution is also influenced by the width of your slit. So we're going to see that also there we have some optimal samplings, what we have to do. But now let's go back to something else that we talked about. Now we know that our sampling has to be proportional to the resolving power, right? So, but now we know that if we have bigger telescope, we have bigger resolving power, which means we have smaller chunks that we have. So our sampling should be smaller, which means that bigger telescope I have, my sampling needs to be smaller. I need to look at smaller surfaces of the sun. I'm getting less photons. And the surface of these chunks is scaling as 1 over d squared, right? Does it make sense? Well, the number of total photons that I'm collecting scales as the square of the diameter of the aperture, which means that the number of photons received per something that we call spatial resolution element is constant. So if you want to make bigger telescope to see smaller objects, your signal to noise is going to stay the same as in the case of your previous telescope. And that's something that you will hear very often from people is they say, okay, we're going to use this telescope as photon bucket. Using something as photon bucket is like a colloquial way to say, we're not going to go to the maximum spatial resolution, but instead we're going to use the fact that we have big telescope to collect more photons to have actually better signal to noise at the same size of the chunk. And that's why in the previous talk I emphasized that bigger telescope means more photons, but only if you keep your sampling the same. And actually Kevin has a very nice slide. I didn't show it today, but I'll show it at some point, where actually also, since you're looking at the smaller chunks on the sun, your exposure has to be shorter because your phenomena travels at the same speed, so it goes through your optical element faster, so your exposure needs to be shorter. So strictly speaking, bigger telescopes have worse signal to noise in some contexts, which is of course not as easy as it sounds, but there are a lot of things that we need to take into account. So yeah, once again, bigger telescope means smaller angular resolution, means more dense sampling in a way, which means you look at the smaller chunks of the surface. Smaller chunks mean less photons, and that is exactly offset by the size of your telescope. So if we want to be, as we call it, diffraction limited, in ideal case, signal to noise or number of counts delivered by Dikis and by some other telescope is going to be the same. And that's why we very often want to have as efficient part between our primary mirror and our detectors as possible, to lose as little photons and to do that to improve our signal to noise. Okay, just very quickly to say that point spread functions and the resolution is more complicated than simply area function. So very often, actually I don't know how it looks with Dikis. I think Dikis has completely clear aperture, right? So this is not so relevant there, but for example, it's relevant to Hinode, and if you are amateur astronomers, it's relevant probably for your setups. Is that when you have these spider patterns or all these things that are there to hold the secondary mirror or some other feature in your telescope, these things contribute to the shape of your point spread function, right? So here you see that your point spread function significantly changes. So you have these very directional maxima in these given directions here, and so on and so on. Right. And of course, in all of them, the primary maxima is the dominant one. But if you have the original image that has very high contrast, and we're going to try and make some of these artificial ones in the next class, even the very far maxima of your area function might contribute there and spoil the situation for you. Right. Okay, so to summarize this, the light that enters the telescope, we can't really treat it only in terms of geometrical optics, we have to treat it in terms of wave optics as well. And to say it in the most simple way, the fact that we don't have infinitely big telescope will cause our images to be smeared. And you will see later that this is further, that actually the much worse effect is that Earth's atmosphere does the same thing. It severely distorts the waveform, right? So strictly speaking, the images that we see are going to be spoiled with respect to the ideal image. They're going to be smeared in some way. However, it's good to know some things about the diffraction, because it's not only a problem, it's also a physical phenomenon that we can exploit for analyzing the wavelength distribution of the light. So basically, both the diffraction gratings and Fabry-Perot interferometers both work on the principles of interference of diffraction. And we're going to see how that is being done in some of the future lectures. So in the next class, we'll actually try to take some real images of, well, actually not real, synthetic images of the sun, but also maybe some real ones. And then we're going to try and we're going to apply various kind of PSFs there, and we're going to see how the things that we see change. We're going to try to create this phenomena of, various magnetic fields canceling each other, and so on and so on. Okay, that was it for today. Questions, comments, critics? Yes, Niraj.
Does the diffraction of the slit in the spectrograph ever cause like spatial smearing?
This causes spatial smearing.
Because like the slit as well has like a finite height, right?
Well, height? Well, the width is much, let me see. The slit has finite height. Yes, it does. But I'm actually not so sure about it. This is a very good question. Because the width of the slit creates, there is diffraction on the width of the slit.
But you want that.
And that one, no, you don't want that.
Okay.
No, you want the diffraction of diffraction grating. In the slit, we're going to see that the diffraction is going to mix up your wavelengths a bit, right? Because it's the spatial diffraction, but then it coincides with the wavelength dispersion that you have, so it mixes wavelengths additionally. Okay, we're going to.
I don't think that's the case, because you have the diffraction when you are in the cube, right? When your object is in the infinity. The slit is in an image plane. It's in a focus, right? I mean, I think
Yeah,
all your
it's-
numbers and all your
it's-
electric field and waves and thing, you can do that when you have
Yeah, when you have the more,
the image, the object when it's at infinity.
Yeah.
There is not infinity, it's there.
So it's like the
Cutting
point
out a
source
piece.
in the slit. That's
Yeah.
what it's equivalent.
Yeah.
Okay.
I think. I could be wrong.
I'm not 100% sure. What do you think?
Okay.
Yeah, I don't know. And there should be,
I mean, like you're recreating your object.
Right.
Your slit is your object. Right. So with no reflection. That is what you have. That's what you have.
You mean you're only cutting out
piece of the image.
a piece of the image, right? So there
Or
can't
the
get
slit is
some-
in a focal plane.
You get some smearing because you have different parts of the image going to the diffraction grating, and there's a wavelength effect there.
Yeah, but he was talking about
Right,
the
the
effect
actual
of the
diffraction,
slit.
right.
That's got a certain size.
Right.
I don't.
I mean, you can't make your slit,
In
arbitrarily
the
large
special sense that you
because-
were talking about.
then you would get the angle from one side of the slit and the angle from the other side to the diffraction grating will be slightly different, but that'll get mixed up with the different wavelengths
Yes.
at
Yeah,
different
yeah,
angles, and you'll smear, your spectral information will be smeared at your detector.
Correct. But that's because you have a different angle of
Of
direction.
the different angles and right from your image plane.
Yeah, that's right. That is a good question. Yes.
So this is more of like a thought experiment type of question. But so is there a scale at which we would expect light emitted from the sun to be coherent? It's like if we build a telescope the size of the solar system, and we're like
yes,
looking at like the
yes,
ion gyro radius.
That's something that I was just thinking about today. I think at that point we would actually have to get into the intricacies of the radiative transfer itself and see, for example, because if you just look at emission as a random property, even two nearby atoms are not coherent. But of course they have to be, because somehow this radiative transfer process must create somehow. Actually, no, radiative transfer itself deals with incoherent light, because you work with intensities all the time. You never work with the electric fields. So I would say that you would literally have to analyze the separate atoms. So basically, what you are looking at when you look at the diffraction is it's very weird, because strictly speaking, you are looking at each atom emits like a monochromatic plane wave in a way, and then you look at all these, and then each of these monochromatic plane wave separately diffracts on your aperture, and you look at the sum of the intensities of all these diffractions, which is for me very confusing, because it's completely at odds of the idea of photons, right? But you could also say that one photon is diffracting, and that then you are accumulating many of them, and you get your diffraction image. It's weird. I really hate thinking like combining quantum physics and this, but we should probably ask some CU people, because I believe that there must be some experts there. But I think to really resolve, like you either need to have because for example lasers are super coherent, because here all the material inside of the laser is emitting coherently because it's stimulated emission. And stimulated emission by nature is a coherent process. And that's why, for example, they are infinitely more coherent than the lamps, which have basically, I know that lamps have coherent times of coherence which correspond to lifetimes of the levels. So it's something super small. But spatially, I'm not sure. I can take a look. That was one of the most challenging classes for me last semester, to like discuss with my students temporal and spatial coherence. More questions? Yes.
Thinking the light bucket effect, I think you see that in real life at the sports games, right? Where those guys, they have those big lenses. They're no longer in focal length, right? I can get an 800 millimeter lens for my camera with a little tiny aperture.
Yeah.
But then my exposures get long, right? So they pay the big money to have the big lens. They're not getting any bigger resolution, really.
Yeah.
I think the biggest effect is then they just get more light
So they go
for
faster.
resolution element, so they can take short
faster,
exposures and they can freeze the action, right?
Yeah.
So that's, those lenses get big not because, wow, they can resolve
Oh yeah, sure.
100 times more on the field. It's because they need more light per resolution.
Yes, yeah. Actually, I never thought about this, but that's exactly right. Yeah. And I mean, also probably, I don't know how the Earth's atmosphere is there on the scale of tens of meters. Probably not very important, right? Well, but you have a lot of people, and a lot of.
What is a typical scale, time scale of a football guy? I don't know.
I mean, they
We're
need,
talking about milliseconds?
yeah.
But they also take all of those
millisecond
things, yeah.
accelerators, right? Like how
Slow-mo shots.
So yeah, they're 800 millimeter f1.4 lenses.
Yeah, okay, cool. So try to bring your computers next time. I mean, we will put everything online and so on, and I will put some data in advance. But basically, the idea next time is that we just look at some more, we look some examples of, finite resolution and how something is improved when we had bigger telescopes, and then we're gonna play with the data. So it's gonna be more relaxed.
I have a very stupid question.
Yes.
Really stupid. Why is Python using that awful color scale? Some of those things are so much clearer in black and white than they are.
No, but it's not related to Python. It's just related to the fact that I like the colors.
Python uses that thing.
I think one of the consequences is that black and white are not. I'm not sure that black and white are using perception. Maybe they remain.
To me, everything looks so weird.
Okay, goodbye to the people online. I'll stop the recording.
During